Dear students, welcome to Solid State Physics. I'm Dr. Pervaiz Ahmad. This is lecture number 8. In this lecture, we are going to discuss about the crystal plane and Miller indices. So let's proceed towards today's lecture about the crystal plane. So just like you can see it here in the figure, within a crystal lattice, it is possible to identify a set of equally spaced parallel planes. These are called lattice planes. So what are the lattice planes? Just like you can see it by yourself here in this figure, this is basically the set of planes and a 2D lattice. So what actually we have here in this, so these are this is the situation within a crystal. So within a crystal lattice, just like I mentioned, it is possible to identify a set of equally spaced parallel plane. So here you can see these are a set of parallel plane. So since these are within the lattice, so that's why we call that lattice plane. In this figure, the density of the lattice point, here you can see density of the lattice point at each plane of a set is the same, and all the lattice points are contained on each set of the plane. That you can see by yourself. Now what about the Miller indices? So Miller indices are basically a symbolic vector representations for the orientation of an atomic plane and a crystal lattice, and are defined as the reciprocal of the fractional intercepts which the plane make within the crystallographic axis. So how we can find the Miller indices for a particular crystal system? So in order to determine the Miller indices of a plane, uh, for that we need the following step. So first of all, determine the intercept of a plane along each of the three crystallographic axes, crystallographic directions. After that, take the reciprocal of the intercept, and finally, at the fractional result, so one have to multiply each by the denominator of the smallest fraction. So these are the three main steps for finding the Miller indices of a particular plane within a crystal. So sample examples would be sufficient to understand the concept of Miller indices. So here you can see we have this particular lattice. So here you can see we have the axes. The axes are being given as x, y, z. Intercept. So here you can see we have the intercept on the x-axis. So the intercept by x-axis is equal to 1. The intercept on y and z, they are infinite, unidentified. That's why we have put it as infinity. So now the second step is to take the reciprocal. So reciprocal of 1 over 1, 1 over infinity, and 1 over infinity. So the smallest ratio when we took, so the for x is equal to 1, for y is equal to 0, and for z is equal to 0. So the Miller indices for this particular plane is equal to as 1, 0, 0. So this is a 1, 0, 0 plane within a particular lattice. We have another example. So here in this example, you see here the x-intercept is 1, y-intercept is 1, and the z-intercept is infinite. It's infinity. So the reciprocal is 1 over 1, 1 over 1, 1 over infinity. The smallest ratio is 1, 1, and 0. So the Miller indices for this particular plane is 1, 1, 0. Example number 3, we have the intercept. The intercepts are 1, 1, 1. Reciprocal 1 over 1, 1 over 1, 1 over 1. The smallest ratio 1, 1, 1. So the Miller indices they are 1, 1, 1. Again, another example is example number 4. So here again we see the intercept. The intercept points on x-axis 1 by 2, and y-intercept so it's the 1, and z is infinity. So the reciprocals, here you can see the reciprocal. So the smallest ratio is 2, 0, 2, 1, 0. So the Miller indices are 2, 1, 0. So it's a bit complicated examples of this plane. So here you can see the intercept A. I mean, for the A is equal to 1, for B is infinity, and for C it's 1 by 2. Reciprocal again, you took the reciprocal and then the smallest ratio. So the Miller indices is equal to 1, 0, 2. So this is another example. One has to proceed in a similar pattern. First you find the intercept, then you take the reciprocal and then the smallest ratio, and in the end within a small bracket you get the Miller indices for that particular plane. So again we have different planes within a crystal. So here you can see if you consider this particular one, so plane intercept axes at 3a dash, 2b dash and 2c dash. So when we take the reciprocal number, so it's equal to 1 by 3, 1 by 2, 1 by 2. So the indices of the plane that we call Miller indices equal to 2, 3, 3, and indices of the directions that is equal to 2, 3, 3. So here you can see these are the plane that we some of the which we already discussed on the previous slide. So here again it's a bit complicated structures, but you can see the Miller indices, which has been calculated by the concept that we mentioned on the previous slide. So here again another examples. So here you can see, and this the intercept, they are being changing one by one. So with that, with changing the intercept, so the plane is also changing. Here you can see with a change in intercept, so the plane is also changing. The intercept is changing. So here you can see the x-axis intercept, y-intercept, z-intercept. So along with that, the plane is being changed. So the Miller indices is totally dependent upon the intercept. You change the intercept. So with the change in the intercept, the planes they are being changed. So these are the difference. Plane depend upon the intercept. So what about if one has indices of a family? So for a family, here is the concept for indices of a family or form. Sometime when the unit cell has rotational symmetry, this is the situation for the rotational symmetry. If we have a rotational symmetry, so as a result of that, we have several non-planar plane that are equivalent by virtue of particular symmetry. So in that particular case, it is convenient to lump all those plane in the same Miller indices, but with the curly bracket. This is a situation particularly for a family or form. When we have family of the plane, so in that particular case we put them inside the curly brackets, and we write it like this. This is a particular situations. This is a family of plane. We have put it inside the curly bracket, that is 1, 0, 0. So the possibility for this family of plane is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1 dash 0, 0, 0 dash 1 dash 1 dash 0, 0. So these are the possible plane or possible Miller indices for a family. And if we have 1, 1, 1, so for 1, 1, 1 we have this sort of the combinations. You can see, you can check it for yourself. And this is, we remember, is the situation when the unit cell has a rotational symmetry. So as a result of rotational symmetry, we have several non-planar planes. So in that particular case, we put them inside the curly bracket, and for such cases the Miller indices might be like this. This situation. So thus indices HKL represent all the planes equivalent to the plane HKL through rotational symmetry. So that's all we have for this lecture. Thanks for watching. See you next lecture very soon. Till then, bye bye.